you're going online in the fall at the Lehman College?
We're 100% online in mathematics in the fall.
Okay.
There is a question of whether there will be some hybrid classes, but at least.
Okay.
Yeah. So we can start again. Our next speaker is Louis-Pierre Arguin from City University of New York. For those of you who are familiar with the City University, you know we have a semi-infinite number of faculty members and a semi-infinite number of mathematicians. And of course, even in the absence of COVID, most of us have never met each other face to face. So I've seen Louis-Pierre on Zoom, but I don't know if we've ever actually been in the same room together. It's possible. In any case, he is our next speaker on large values of zeta in short intervals. Please.
Thank you, Mel. Thank you for the opportunity to speak. So yeah, this talk is a bit in the same flavor as the previous one. It's about the large value of zeta in short interval. And as Emma said, so that's related to conjecture of these three people, Fyodorov-Hiary-Keating. So what I'm going to talk about is one theorem that is joint work with Paul Bourgat at NYU. He's also a probability person like me. And we teamed up with a number theorist, Maxime Radziwill. All right, so just to get things going, all right, so here's a graph of the modulus of the Riemann zeta function on the critical line. So everything is going to be on the critical line. And that's the modulus, right? So what you have is a very oscillatory function. That's not surprising because you have pick up every phase of the integers. And what we would like to understand are not the zeros, but the large values, which is a hard question as well. So what are the big problems for this question? So large values of zeta on the critical line. So you have the Lindelof hypothesis, right, that tell you that zeta should grow no faster than any power of t as you move along the axis. All right, and so any power, and the world record is Bulgarian 2017, so we know that that power is less than 13/84, which is the interpolation between 1/6 and 1/7, 1/6 being the big wall to break. Now, if you assume the Riemann hypothesis, you get something better. So how better? You have exponential of certain constant log t over log t. So if you do the math, right, that's like t to the power 1 over log t. So you're doing a bit better than this epsilon. This is going to 0. Now, a very hard question, though. So these are obviously very hard questions. And another interesting question is to see, well, that's big O. So what is the actually true order of zeta? What is this envelope? And well, there's, I guess, two competing scenarios. The first one being that it grows, that the Riemann hypothesis gives you the correct bound. So it's called that the theorem of 1. And the second scenario is by Farmer-Gunnick use, and they have this nice paper where they give several arguments in favor of this conjecture, says that actually the power in this log shouldn't be 1, but if I look at the maximum over a long interval, the true order should be square root of that log, and there's some correction. Scenario 2, right? So this is 1 versus 1/2 scenario. So these are the hard questions. So now the idea of Fyodorov-Hiary-Keating was to simplify the question. And instead of looking at the global maximum, this envelope, well, let's look at the noisy part here. So let's take a point, right? And the point is going to be tau in all my talk. I'm going to change this. And what you want is to look in the neighborhood, right, of a given point and see how high can zeta go. in the neighborhood. And then you can play with the size of that interval if you wish, with the hope that maybe you can capture big intervals. All right, but you start with a simpler question of looking, in that forest there. So that's what they're doing. So how does that look like? So here this picture is log zeta, not the modulus of zeta. So the zeros are sent to minus infinity. Those are what you see here. And so you just zoomed on your function. And what you pick up, what you see is something like this. So you start picking up some regularity, and the order of the regularity, that's going to be important later, right? So the width of these peaks are essentially the peaks. So it's the width of the distance between the zeros, which we know should be around 1 over log t, where t is where you look at, okay? And so if you zoom, so you fix an interval at a certain size, and what you're interested in is, well, can I say something about the largest peak here? What's the order what's the order of the magnitude of that peak? So that's the question that Fyodorov-Hiary-Keating asked. And so to be precise, you're going to pick a point. So in fact, we're going to pick it not on T2T, but on not on T0T, but on T2T for technical reason, like Selberg, and look in the neighborhood of that point. So here's a conjecture. Actually, Emma had it on the slides. So that's from 2012. So what are the large values in a typical short interval? So what I mean by typical is, again, you pick a point at random on your axis, okay? And then you look around it. So that's what I mean by typical. And short, what I mean by short is you pick an interval of order 1, okay? But you can play with that length if you want. So let's start with order 1. So what is the order of magnitude? That's to be compared with the order of magnitude I showed before, right? So at the leading order, you pick up a log t. Then in the subleading order, you get log t to the power 3/4, and that power has a lot of information, as I will explain. And after that, there's no more correction. What you pick is the order 1 fluctuation. So obviously you have fluctuation here. The randomness is only in the point you pick on the axis, okay? But how will the maximum fluctuate as you pick different points on the axis? It's going to be something of order 1, okay? So this constant is of order 1 in the sense that if you take the sequence of, so for every t, as t goes to infinity, I get a sequence of random variable, it converges. So these fluctuations can be understood supposedly, and you even have some idea of the distribution of these fluctuations. And the information that you should have is that the right tail, in the sense that these fluctuations for large values should go like y e to the minus 2y, okay? So again, there's two things that are surprising here, is the precision of the exponents, the 3/4, and as well for probabilities, this y is a bit strange. Why is it strange? Because what you would expect is something like an exponential decay, okay? So that's the conjecture from 2012. So as Emma explained, this is related to a problem in random matrix theory where you look at the characteristic polynomial and you have the same conjecture. So in fact, that's how they came up with the conjecture. You can do more calculation in random matrix theory. You apply the correspondence between random matrix theory and zeta, and it's, of course, the belief, I guess, that these two things are related, and you have it, right? So here's a theorem I want to present. So we can actually prove these things fairly precisely now. That's a theorem with Paul and Max. So again, you pick a typical point on the axis, and for any y, you have the following thing. So again, so the probability here is just picking a point on the axis, okay? So if I pick a point tau on the axis uniformly on T2T, and I look at the maximum in an interval order 1, what's the probability that it goes beyond this threshold of log t over 3/4 log t and a certain constant, well, it decays like y e to the minus 2y, okay? So we have exactly the correct upper bound for this, even with the tail, okay? Now, it's important to, sometimes when you put a probability in a statement, you know, you feel that you're losing actually content and, you know, things are random, but I mean, this probability again has a precise meaning because since you pick that point uniformly, you're talking about the Lebesgue measure of points, right? So this statement you can translate as the Lebesgue measure of points on the interval T2T, for which when you look at the maximum as an interval, well, this measure cannot be bigger than T y e to the minus 2y, okay? All right. Now, let me just say a thing. I'm going to add something to my slides that this question is related to the question of the maximum and the large interval, y. So we can prove this for any y, okay? That's good. But what you would like to have is even add a precise correction, which is Gaussian here, log t. Okay, so why is that important? Let's say you have this, so we don't know if we have this, but if you have this, this would be in favor of the scenario. So I had the scenario 1 and 2, right, for the large value. Scenario 1 would be the Riemann hypothesis bound. So that's scenario 1. If you have an exponential decay, then actually you can just look, if you look at the maximum and interval of order 1, well, that tells you something about large intervals because you can just chop your large interval in several intervals of order 1, and the maximum over all of them is, you know, the maximum so the maximum of the big interval is the maximum of all these maximums together. So you could say something. So if the decay is this for large y, then scenario 1 wins. If the decay is actually Gaussian, so for large y, if you have this, this is going to win. And that would be the Farmer-Gunn-Accuse with the square root of log t. Okay, so that would be a larger decay. So we cannot do this, but we do have the exponential. Actually, we have this, but not for all y's. We had it for y. So that's the relation with the large question. Now, let me just say something about how you can prove these things. So, all right. So the one important part of the heuristics is the Selberg central limit theorem that Emma mentioned. So here you're just looking at the value at a typical point, not the maximum in the short interval. And Selberg tells you that, well, log of the modulus of zeta behaves like a Gaussian with a variance of 1/2 log t. Why is this true? And that's going to be important for the rest, for the idea of the proof. So how can you prove this central limit theorem? Well, you go back to the Euler product of zeta, okay? So formally, if I take the log of that, this becomes the sum over prime. Okay, just take the log of this, the sum over prime, and then you expand this and you look at the first order. That's what you pick up. Okay, so obviously I cannot do that if I'm on the critical axis, but essentially the proofs are about showing that, you know, that this essentially is true by adding a truncation with some error term that you can control. Now, this tells you that, well, you have a sum of random variables here, so this is close to CLT, if those random variables are independent. And turns out, so if I look at this p to the minus I tau, those are actually random variable on the unit circle, right? With different phases, different frequencies. And turns out that they're essentially independent when you compute the moments, all right? So heuristically, at least, this is like a sum of independent random variables. And what about this variance from Selberg? Well, you can take the square of this. If you take the square of this, you get 1/2 from the real part, and you get the sum of 1 over p from the square of the square root, and it's just a diagonal term that you pick up. And using the prime number theorem, you know the density of prime, so it's 1 over log right? So what you pick up, this sum is like the integral of 1 over x, 1 over log x, which is a log, and that's why you get this variance, okay? So the important point, again, is if you want to prove Selberg's CLT, is to realize that the log of zeta is actually a sum over prime of these random variables are almost ID. Now, where does the priority come from? Well, we just saw it that, well, you have a sum of independent random variables. So you have something like a random walk, okay? So I'm going to define SK to be the sum over prime up to the exponential of k, which makes sense because as we saw from here, from the variance, right, the right scale for the variance is log. So if I want a variance k, right, like a random walk, SK should be, you know, a multiple of k for the variance because I add up things. So this is the right scale for my truncation. And these are my random variables, okay, my increments. And the k should go up to log t because, well, this is what Selberg's tell me that the right variance is 1/2 log t. Okay, now, okay. So you can, this is like a Dirichlet polynomial, so you can compute the moments fairly easily, okay? And what you get is that if I take the 2q moments of that, what you're gonna get is Gaussian moments. So this is not, it's fairly elementary to do that. And the variance is k over 2, okay? Because that's how you design things. And the important thing is you have an error, okay? You have an error, which is exponential of ek, which comes from that truncation. 2q is the moment, and 1 over t, okay, which comes from this, the width of the interval. So if you can make this error small, okay, then the moments are essentially Gaussian, and you can start doing probability. Now, there's 2 hurdles to the proof to get the large values of the maximum. That's what I want to explain in the last 5 minutes. So the first hurdle is actually dealing with the error, okay? Because what you would like to do, right, is to have a fairly long Dirichlet polynomial. In other words, you want to push that k close to log t, so you want the primes to go up to t. The problem with that is that, well, you can do that if 2q is small, if you push k close to t, okay? You can do that for q small, but not q that depends on t too much, because then, you know, you might get an error which is large. So, and the problem is if you want to do deviation, so the maximum of log zeta should be of the order log t. So you want actually moments which are of the order of log t. And then that's a problem because you want k large and 2q log t, and they are explosive, okay? So that's the first hurdle. The second hurdle is the fact that you have to know something more if you want to pick up the 3/4 I was explaining. Okay, why is that? If you do a naive proof using a union bound, so you know that an interval of order 1, you have log t 0, okay? Because as I said before, the gaps between the zeros of 1 over log t, and if you look at the maximum, I just have to look between the zeros. So essentially, I can discretize the maximum on log t points. So if I do a naive proof, a union bound, so the maximum bigger than v, I have log t point is smaller than log t times the probability that one point goes is beyond v, and then I just use Selberg, okay? I don't know if I can apply it to these regime, but let's say you can. Then what you get for the order of the maximum is not 3/4, okay? So if you try to match this to get something of order 1, what you're gonna get is 1/4, which comes from, which essentially cancels the square root, okay? So you don't get a 3/4. So you have a missing 1 over log t. If you're only interested in the leading order, this log t, then you'll find doing this kind of union bound, but not if you want the order of, you know, finer asymptotic. So here's the most important slides, I guess, on this talk. So what you want to understand how zeta produce large values in a small interval, and that should be also hold to larger interval to some extent. So what's the strategy? Okay. So what's my axis here? This is the prime axis. So in the log-log scale. So we know that zeta is pushing primes up to t. Okay. So in the log-log scale is log-log t. So this endpoint is log zeta. Okay. And this axis is the prime. Okay. So in the log scale. Okay. And I'm looking at this random walk sk, which represents, this Dirichlet polynomial for every prime at the scale e to the k up to t. Okay. So how can you achieve this large value, which is an order log t, and which is maybe a subleading order? So you have to understand what is the contribution of every prime to achieve large value. Are the small primes involved, the large primes, or everybody is essentially contribute the same? So the log-log scale turns out that it's linear, so every prime essentially contributes the same. So you grow linearly, this sk grow linearly. But there is some corridor, some narrow corridor here, and that's essentially the core of the proof to show that this corridor exists. Okay, so sk, these random walks, must lie in a narrow corridor at all k. So this is good because it helps you going over the two hurdles. So once you have this corridor, what happens, and this corridor has width, okay? So if I'm close to log t, whoops, I'm sorry. All right. So if I'm close to log t, okay, and I subtract, so I'm close to log t, and I subtract iterated logarithms. So in other words, I approach log t by iterated logarithms. Then the width is essentially this logarithm iterated L plus 2 times. Oh God, I'm so sorry about that. All right. So why is that good? Is if I know that I'm in this narrow corridor, then you don't need very large moments to handle the random walks. What you need is essentially when I look at an increment which is close to k log t, so which is close to zeta, well, you just have to handle like very small value, which is iterated log of t. Okay, so in a nutshell, these moments can be much smaller for the increments where you are very close for prime, very close to t. Okay, so you handle this error. And the last thing I will end on that, the second hurdle is where this three-quarter occurred and not 1/4. And the reason is, if I have this picture again, how you produce values in this Dirichlet polynomial. So it's linear, but you have an upper barrier in this corridor. So this random walk is not actually an exact random walk. It's a random walk that avoids a barrier. And there's a nice theorem in random walk called the Ballot theorem. It's a combinatorial result that tells you that a random walk that avoids a barrier, which is close enough, the probability is 1 over the length of the random walk. And in our case, the length is log t. And so that gives you the missing factor, so that 1/2 plus 1 is 3/2, which ends up canceling the 3/4. All right. So I will skip how you actually construct that corridor, but that's the core of the proof. You have to actually do a recursive scheme. And for the lower corridor, what is important, I just say, is this twisted fourth moment. So that's an input from number theory is very important. And these techniques can be extended to intervals that are power of log t, like Amit said, but you cannot go beyond intervals that are with power of log t, okay? So, and the reason, again, is this error. Let's say you want to do a power of t and then a power of log t. What happens is this error, you need moments that are way too large for this error to be small, and so all this Gaussian behavior is lost. All right. Thank you very much for your attention.
Thank you, Louis-Pierre. Are there any questions for our speaker?
I think Mel, you're muted, or it's
Oh,
me.
sorry.
No, Mel wasn't muted. I heard him before. Now you're muted, Mel.
I will do it again. Thank you, Louis-Pierre.
Okay.
And are there any questions for our speaker? I can look in the Q&A. I can look in the chat. I can see if anyone has raised a hand.
I have a hand raised, but I don't know if it's Max. I think has a hand raised.
Oh, yeah, Max. So Max, if you have a question, you can talk. If not, then I thank Louis-Pierre again for his talk.
There was a question, the attendees. I don't want to.
Sorry, I can't hear what you're saying.
Oh. I think there's a question in the panelists and a question in the attendees, but I don't know if.
So, Max, you can speak, yes? Well,
I can answer the question by chat if you just don't want.
Okay, good. So thank you very much, Louis-Pierre. And the next talk will be in 2 or 3 minutes.